Imagine grinding this massive steel drill bit miles into the dark, crushing crust of the Earth.
Yeah.
You know, you're plunging through these layers of rock that haven't seen the light of day for hundreds of millions of years.
Right.
And instead of just pulling up oil or natural gas or water, you're pulling up data, like mountains and mountains of data. A single drilling operation, just one well, can generate 10 terabytes of data every single day.
Yeah, and to put that 10 terabytes into perspective, that is basically the equivalent of a massive enterprise data center's daily output.
Wow.
It's just this absolute ocean of high-frequency telemetry, acoustic measurements, temperature gradients, pressure differentials, all of it generated by one piece of metal grinding through dirt and rock.
Right. You are essentially downloading the equivalent of, like, thousands of high-definition movies every single day.
Exactly.
Just from a single hole in the ground.
Yeah.
And the geologists, the highly trained scientists tasked with figuring out exactly where to drill and how to navigate those subterranean hazards safely, they're just absolutely drowning in this data.
Completely drowning.
Which brings us to the core mission of our deep dive today. We are exploring how the oldest, most physically grinding industry on Earth is currently forcing the evolution of the most cutting-edge tech in cloud computing and artificial intelligence.
It's really a fascinating collision of two completely different worlds.
Yeah.
On one hand, you have geophysics, right, which deals with mud and steel, heavy machinery, immense physical pressure. And on the other hand, you have generative AI, neural networks, limitless cloud compute.
It's wild.
And what we are seeing right now is that the tech industry is essentially stepping in to rescue the energy industry from its own data deluge.
I don't think rescue is an overstatement at all. Let's look at this massive S&P global survey we have here. The numbers paint a frankly terrifying picture of what a modern geoscientist's day actually looks like.
Oh, absolutely.
Like 1/4 of geoscientists right now spend over 80% of their time just manually collecting, checking, updating, moving, and formatting data. 80%. You have people with literal PhDs in earth sciences spending their entire work week wrangling corrupted files.
It is a catastrophic misallocation of human capital. You are paying top-tier scientists to basically be glorified digital filing clerks.
Right.
And the reason this happens is compounding. That same S&P brief notes that 68% of upstream oil and gas companies, so the ones actually doing the exploration and drilling, they're using more than 5 different geology and geophysical applications. The industry calls these G&G apps. And 16% of these companies are juggling more than 15 different applications for their day-to-day processing.
Okay, I want you, listening to this, to just imagine trying to do your daily job while being forced to constantly switch between 15 completely different software ecosystems.
It sounds like a nightmare.
It really does. Imagine writing an email in one program, but you have to convert it into some proprietary code just to attach a spreadsheet from another program, and then the second program refuses to read the text from the first.
Yeah, and it's only going to get heavier.
Right.
The survey points out that 60% of G&G professionals expect their data volumes to grow by anywhere from 15 up to 49% in just the next 2 years.
That's insane. So you simply cannot sustain that level of exponential data growth on legacy localized IT systems.
You can't. The infrastructure is hitting a hard breaking point.
Yeah.
When highly paid experts are waiting days or even weeks for data to be formatted, the results of their analysis are heavily delayed.
And time is money, right?
Exactly. In an industry where a deep water drilling rig can cost, $500,000 a day to rent.
$500,000 a day.
The ripple effect of delayed decision-making translates into millions of dollars in wasted capital very quickly.
So you can't just run out to the local electronics store and buy more hard drives. You have to fundamentally change where the data lives and how it breathes. And that thought process naturally leads companies to look at cloud migration. But, and I really want to pump the brakes here, because moving to the cloud in the energy sector is not the magical, frictionless fix that tech evangelists often claim it is.
Far from it. Moving to the cloud is the required foundational step, absolutely.
Right.
But the subsurface industry faces incredibly specific, highly unique challenges that a standard corporate cloud migration never, ever encounters.
Right. And Boston Consulting Group, BCG, actually laid this out beautifully. They identified 8 specific, massive data challenges that oil and gas companies face when trying to modernize.
Yeah, they really nailed it.
Let's really unpack these, because it shows exactly why geoscientists are pulling their hair out. First up on BCG's list is variety.
Right, the sheer variety of data formats in this space is staggering. I mean, in a normal company, you have what? Spreadsheets, text documents, maybe some video
Yeah,
files.
standard stuff.
But in geology, you have highly technical real-time drilling logs streaming in by the millisecond. You have massive acoustic seismic surveys that look like complex sound waves.
Right.
You've got laboratory core sample chemistry and incredibly dense 3D and 4D reservoir models. And all of this scientific data sits right on top of these standard corporate transactional data. It's just a chaotic mix of structured and completely unstructured information.
Which leads right into the second challenge. Proprietary formats. Because if you have all this variety, you'd hope they all at least play nice together.
Oh, they do not. Not at all.
Yeah, I figured.
Historically, the software vendors in this space use proprietary formats as a deliberate business strategy.
Ah, of course. Lock them in.
Exactly. If a 3D geological modeling software generated a file, it was locked into that specific vendor's ecosystem. It required highly specialized conversion tools to move it anywhere else. And honestly, often you lost critical metadata in the translation anyway. So frustrating. Then you have the third challenge: dataset sizes and volumes. We talked about the 10 terabytes a day from a drill bit, but BCG points out that a single large-scale seismic survey, where they send those acoustic waves deep into the earth across hundreds of square miles,
Yeah.
that can easily reach into the petabytes, and a petabyte is 1,000 terabytes.
Right. It's massive.
That stretches the network capabilities of even the absolute biggest cloud service providers out there, like AWS or Azure.
It really does.
Mm-hmm.
And fourth on their list is scarcity and interpretation.
Yeah.
Now, this is a very subtle but critical problem.
Okay, break that down for me.
Unlike a manufacturing plant where, every variable is perfectly measured by a sensor, the Earth's crust is an unknown.
Right.
Technical data is often limited, sparse, or incomplete. You might drill a well here and another one 2 miles away, and you essentially have to guess what the rock looks like in between.
Because the data is scarce, it is highly subject to human interpretation. Two geologists can look at the exact same data set and draw two completely different maps of the subsurface. There is rarely a single definitive source of truth.
Wow. Okay, fifth is stakeholder requirements. And this makes sense. It's not just one company looking at this data. You have national governments, environmental regulators, specialized subcontractors, joint venture partners.
Yeah, it's a very crowded room.
Right, and they all have incredibly complex, overlapping contractual commitments, export constraints, and strict confidentiality rules about what specific data can be shared, when, and with whom.
Exactly. And that flows right into the sixth challenge: ambiguous definitions.
Yeah.
Because you have all these different teams and external partners, they often apply entirely different naming conventions and data definitions.
Oh, that sounds like a mess.
It is. One team might label a specific layer of sandstone one way, and another team labels it something entirely different. This ambiguity stops people from being able to reuse or trust shared data sets. If you cannot establish a uniform dictionary for the entire company, your data becomes practically useless to anyone outside the immediate team that generated it.
Which brings up the seventh challenge, organizational complexity. Because these are massive, decentralized global corporations.
Yes.
They operate with local joint ventures in West Africa, the North Sea, the Permian Basin in Texas, and the local IT teams in those regions have their own budgets and priorities that frequently clash with the central corporate IT directives in, say, Houston or London. It creates fractured data ownership.
And finally, the eighth challenge, which is uniquely physical: location and bandwidth.
Yeah, this one was huge.
You are generating these petabytes of data in the absolute most hostile, remote environments on the planet. You are in the middle of the deep ocean on a floating rig, or deep in the Saharan desert where broadband internet simply does not exist.
You can't just connect to the local Wi-Fi.
No. You cannot just seamlessly upload 10 terabytes to the cloud over a satellite connection that drops out every time it rains. It requires highly intelligent, localized edge computing and replication methods.
So when you look at that 8-headed monster, the sheer size, the proprietary locks, the awful bandwidth, the fragmented teams, you start to see why massive IT companies are stepping into the ring.
Oh, absolutely.
They're looking at this and saying, hey, we can build specialized hardware for this.
Mm-hmm.
Like, for example, look at the collaboration between NVIDIA, Lenovo, and the Geocomputing Group. They partnered up to create a absolute beast of a machine called Riva, the remote interpretation and visualization appliance.
Yeah, Riva is a brilliant piece of targeted engineering. It is a high-performance computing platform specifically tailored for the heaviest subsurface workflows. Things like rendering petabytes of seismic analysis and running complex fluid reservoir simulations.
And it uses some serious hardware, right?
Oh, yeah. It integrates Lenovo's enterprise servers and storage architecture directly with NVIDIA's RTX GPUs and InfiniBand high-speed networking.
And the performance metrics on this thing are wild. Geoscientists who switch to using Riva can access and interact with their massive data sets 50 to 100 times faster.
It's game-changing.
Oil and gas companies deploying this kind of centralized, private cloud compute model have reduced the time it takes to get their IT infrastructure into production by up to 70% compared to building traditional, piecemeal IT setups. They're reporting a 100 to 400% return on their investment in less than a single year.
And, that massive return on investment comes entirely from curing that productivity drain we discussed earlier.
Right, the 80% manual labor thing.
Exactly. The NVIDIA technical blog highlighted that up to 40% of a geoscientist's time is often wasted just staring at a loading bar.
Ugh, the worst.
Just waiting for massive 3D models to render or waiting for legacy applications to respond to a simple query. When you migrate that heavy data to a secure data center equipped with a centralized, hyper-accelerated compute model, your scientists can suddenly iterate their ideas without those crushing delays.
There's another great case study from NetApp. They worked with BDO, which is the leading utility operator in Turkey. By migrating their infrastructure to scalable, all-flash storage, which retrieves data exponentially faster than older spinning disk drives, they could finally keep pace with their exploding data requirements.
Yeah, flash storage makes a huge difference.
And NetApp is executing similar strategies with CGG's proprietary Geovation software. They're taking raw, chaotic data streaming from hundreds of thousands of individual acoustic sensors spread across the globe, funneling it into subsurface imaging centers, and processing it to create these unbelievably precise 3D maps of the Earth's crust.
But we really need to pause here for a second.
Okay.
Because moving your data to the cloud, buying all flash storage, setting up centralized servers, that all sounds fantastic. But there is a massive, very expensive pitfall that the industry publication GeoExpro refers to as the lift and shift trap.
Ah, the lift and shift trap.
Yeah, and it is something almost every company gets wrong on their first try.
Okay, I want to make sure I understand this perfectly. Is lifting and shifting legacy software to the cloud, basically like buying a multi-million-dollar Formula One Ferrari, parking it in your suburban driveway, and only using it to sit in the air conditioning and listen to the radio?
That is a highly accurate analogy, yes.
Okay.
If an organization simply takes their existing legacy data structures and their old linear workflows and just drops them onto an Amazon Web Services or Microsoft Azure cloud server, they are essentially just treating the most advanced computational network in human history like a really big remote hard drive.
Right.
You might save a fraction of a cent on physical server maintenance, and your files might open slightly faster, but you are completely ignoring the transformative power of true cloud-native technologies.
Because that legacy infrastructure, the software they've been using for 20 years, it was built with a totally different physically constrained mindset.
Yeah, exactly. You have to look at the history of the workflow. Current geoscience applications were designed around the severe physical limitations of the workstation tower sitting under a geologist's desk in the early 2000s.
Those big clunky towers.
Right. And seismic data has always been huge. So in the past, the duration of an entire exploration project was completely dominated by the critical path of computation.
Meaning the computer was the bottleneck.
Exactly. A geophysicist would set a complex algorithm to run on a block of seismic data, and then they would literally go get coffee or just go home for the entire weekend because the physical computer could not process the math any faster.
So the human workflow, the actual day-to-day behavior of the scientist, evolved to accommodate how slow the machine was. They worked in small, isolated chunks.
Precisely. They would carve out tiny, manageable pieces of data, process them slowly, and stitch them together. But once your data lives in the cloud, utilizing near-limitless compute power across thousands of synchronized GPUs, that physical limitation ceases to exist. If you just lift and shift, you are deliberately running old, bottlenecked, staggered processes on limitless engines. You have to fundamentally rethink the workflow itself. GeoExpro poses a brilliant question to the industry. What would you actually do if you had unlimited compute power?
Right, because you wouldn't just do the exact same localized tasks slightly faster. You would zoom out. You would do entirely new, massive scale things.
Yes. Instead of analyzing one tiny fault line over a weekend, you could execute standardized, simultaneous processing over your entire global portfolio in an afternoon.
Right.
You could instantly run direct visual comparisons between massive seismic volumes from the Gulf of Mexico and the coast of Brazil. You could take decades-old low-resolution data and reprocess it using the absolute latest physics algorithms in hours instead of years.
Which really brings to mind what Blueware is doing with their VDS adaptive streaming technology.
Yeah.
They realize that downloading petabytes of data from the cloud to a local screen defeats the purpose. So they embed their cloud-native data format directly into modern interpretation applications, like Elias's Paleoscan. You aren't just storing the data in the cloud. You are streaming massive, interactive, 3D subsurface data sets directly from the cloud. Exactly like how you stream a 4K movie to your TV without downloading the whole file first.
And that level of fluid interactive streaming brings us to a massive structural roadblock.
Okay, what's that?
Having limitless compute power and amazing streaming infrastructure in the cloud is technically wonderful, but it means absolutely nothing if the data itself is speaking 50 different incompatible languages.
Oh, right, the proprietary formats.
Yeah. If your drilling department's software is written in a code that your reservoir engineering department's software cannot read, that limitless compute power just slams into a brick wall.
Which transitions us perfectly into the great babblefish of geology. We've built the superhighways, but none of the cars can actually talk to each other.
That's a great way to put it.
This is the desperate need for industry standardization, specifically the Open Subsurface Data Universe, or OSDU.
The OSDU is, without exaggeration, arguably the most important structural shift happening in the global energy industry's IT landscape today.
Let's clearly define what this is for everyone. The OSDU is a massive cross-industry collaboration. It's a cloud-native, open-source, standards-based, technology-agnostic data platform.
Right.
In plain English, it is a monumental agreement across the biggest, most fiercely competitive players in the energy sector to finally standardize exactly how data is ingested, cataloged, and executed.
And to truly understand why this is revolutionary, you have to look at how exploration and production, or E&P companies, have traditionally organized themselves.
Okay.
They exist in extreme, highly defensive functional silos. You have the exploration team mapping the rocks. You have the drilling team designing the physical well. You have the completions team figuring out how to fracture the rock. And you have the reservoir engineers calculating the fluid dynamics over 20 years.
All set.
Historically, each of these individual teams owned their own specific data, locked in their own siloed database, almost always using entirely different software vendors.
It's like trying to run a massive multinational corporation where the accounting department speaks only French, the marketing team speaks only Japanese, and HR speaks only Swahili.
Exactly.
And the CEO is just sitting there wondering why it takes 6 months to approve a basic budget.
And the financial cost of that lack of internal communication is staggering. To build an accurate model of the Earth, a geoscientist desperately needs all possible sources of data to refine their analysis.
They need the whole picture.
Right. They need real-time data from similar geological basins, historical interpretations, and deep petrophysical studies. But if they do not have visibility into the reservoir engineer's silo because the software is incompatible, they're making multi-million-dollar decisions with blinders on.
Yeah.
The S&P brief we looked at earlier explicitly noted that 60% of upstream organizations admit they do not have efficient data sharing between their own internal domains.
Okay, I really have to stop and push back on this here, because this sounds completely irrational.
It does.
If the industry is losing billions of dollars to these data silos, suffering massive delays in drilling programs, and experiencing huge exploratory cost overruns because the drilling team literally can't read the geology team's files, why on earth did it take a massive consortium to finally agree on a standard like OSDU?
This is a very fair question.
Why wasn't this done 20 years ago? These are companies that are normally obsessed with efficiency. What forced their hand now?
Well, it really comes down to the economics of software monopolies. Standardizing complex, multidimensional physical data is incredibly difficult, technically, sure. But more importantly, proprietary lock-in was unbelievably profitable for the major software vendors for decades.
Follow the money.
Exactly. If a vendor controlled the specific proprietary format of the data, the oil company was essentially held hostage. They were locked into endlessly renewing licenses for that specific vendor software, because if they switched, they would lose access to 20 years of their own historical data.
Wow. So the software companies had literally zero incentive to build bridges.
Exactly zero. But the sheer velocity of the data deluge we talked about earlier finally broke that business model. The volume simply got too big, and the operators, the massive energy companies actually paying the bills, demanded a change.
They had enough.
Yeah, they banded together and forced the creation of OSDU. It provides a single, uniform data fabric. When data flows freely across a standardized open-source platform, it completely eliminates the need for costly, error-prone, and time-consuming data transfers between different proprietary applications.
And the ripple effect of that standardization is massive. SMT points out that when you standardize the foundational data platform, you suddenly democratize software choice.
Yes.
You aren't locked into one giant monolithic vendor's ecosystem anymore.
Yes.
Smaller, highly specialized, innovative AI startups can build fit-for-purpose tools that plug and play perfectly into the system because everyone finally agrees on exactly how the data will be formatted.
It creates a vibrant ecosystem of innovation. And this agility is absolutely vital for the modern, fast-paced energy landscape. Bain and Company published a brilliant brief on big data analytics in oil and gas, and they highlight the rise of unconventional shale wells as the prime example of why speed is necessary.
Unconventional
Yeah,
wow.
like the fracking boom in the U.S. It requires drilling vast numbers of wells incredibly quickly. Decisions must be made daily, right there in the field, often without the luxury of involving the central corporate functions in Houston.
Right, the handoffs for a single modern shale well are relentless. You are bouncing constantly between geology, drilling, completions, construction, land acquisition, regulatory compliance, and production teams.
It's incredibly complex.
Bain points out that a single operator might have hundreds of these wells actively drilling at the exact same time. If your operating model relies on rigid, slow-moving functional silos, the entire machinery just grinds to a halt under the speed required.
Exactly. And Bain points out a very specific, almost ridiculously mundane problem that completely ruins this fast-paced environment: the lack of uniform well identification numbers across different IT systems.
How interesting.
Sounds trivial, but consider this. If the finance department uses one ID code to track the budget for a specific well, and the operational software collecting the daily geologic data from that same well uses a slightly different alphanumeric code, the data remains isolated.
Right, the systems can't match the money to the rocks.
Exactly. The whole analytical engine stalls because you cannot automatically track the metadata.
It's the Babel problem at a micro level.
Mm-hmm.
Like a single typo ruins the algorithm.
Precisely. But once you implement a rigorous, industry-wide standard like OSDU, those internal silos collapse. You finally establish a single version of the truth. The drilling telemetry, the completion fluid data, the massive seismic logs, the financial spend, they are all woven together uniformly and instantly available to the decision makers on the ground in real time.
And this is the major turning point in our deep dive. Because once that data is centralized and standardized and cleaned of errors, it is finally ready to be read and analyzed by intelligent agents.
Yes, the table is set.
Which leads us out of the foundational infrastructure phase and into the really mind-bending stuff: generative AI and the desk analysis revolution.
This is the frontier where we see artificial intelligence fundamentally changing the minute-by-minute reality of the human geoscientist. We are moving from just organizing data to extracting profound insight from it.
Okay, here's where it gets really interesting. For you listening, I want you to think about having an army of genius intern librarians. And these interns don't need sleep.
I'd hire them.
Right. They can read through 50 years of handwritten field notes, scan PDFs, smeared faxes, and muddy drilling reports in about 3 seconds. And not only can they read it, but they can cross-reference it instantly and spot exactly where someone made a critical mathematical mistake on a Tuesday in 1982.
That is an amazing visual.
That is essentially what large language models, or LLMs, and specialized generative AI are doing right now for desk analysis.
It is a profound, almost unimaginable shift in how historical data is utilized. Historically, a major exploration team might have decades of data locked away in completely unstructured formats.
Like what?
We're talking about old, unsearchable PDFs, physically typed end-of-well reports, scanned core logs, and, yes, literally handwritten field notes from geologists who retired 20 years ago.
Oh.
That data is incredibly valuable because it documents the physical reality of the Earth, but it has been practically inaccessible because it would take thousands of human hours to manually read, correlate, and digitize it.
Enter platforms like RadExplore. They literally market themselves as the Google for geology, and Honestly, it's a perfect description.
It is highly accurate. RAD-Explorer is built specifically to search, analyze, and extract insights from millions of unstructured geological documents simultaneously.
And it's smart about it.
Very. It isn't just a basic keyword search. The AI is trained extensively on the complex, highly specific terminology and contextual language of the geological and geophysical sciences.
In their recent updates, they rolled out some incredibly heavy tech. They introduced hybrid extractive search.
Yes. Hybrid extractive search combines traditional rigid keyword searching with AI-driven semantic contextual search.
How did that work in practice?
Well, if you search for the word fracture, a traditional system only looks for that exact word. The hybrid AI understands the context. It looks for terms like fault, fissure, shear zone, or cleavage, understanding that chemically or physically, they might represent the exact same risk profile the engineer is looking for.
That is so smart. And they combine that with fuzzy OCR optical character recognition and advanced numerical search, which is specifically designed to read those old, messy, smeared 20th century scanned reports where number 8 might look like a B or a 3.
The technological leap here is the capability to process entire massive data sets through what we call long context windows. An advanced LLM can now digest an entire 500-page historical end-of-well report, which includes text, charts, and tables, and immediately generate bulleted summaries.
It just reads the whole thing at once.
Yeah, and it can formulate standard operating procedures or even build presentation slides based on that structured input. It extracts the signal from the noise instantly.
Look at what the Platform Well database is doing. They have built an interface that covers practically every well ever drilled in the United States and Western Canada.
It's a massive database.
Over 40 million individual files aggregated from dozens of different state and private sources. And they're integrating Gen AI directly into the interface so users can essentially chat with their wells.
Which is such a cool concept.
You don't need to know SQL or complex database coding. You can literally type in plain natural English. Show me all horizontal wells in the Permian Basin that had peak oil production over 1,000 barrels a day, where the frac stages were greater than 40. And the AI instantly translates that conversational sentence into incredibly complex database filters, pulling up map views and production curves instantly.
And if we step back and connect this to the bigger financial picture, think about the sudden monetization of that historical data. In the past, those decades of old drilling reports were viewed purely as a storage expense.
Right, they were just sitting there.
They sat in dusty physical filing cabinets or took up space on legacy hard drives doing absolutely nothing.
But now, because the AI can read them and understand them,
Now they are transformed into a highly valuable, actively licensable asset. There's a brilliant specific use case highlighted in a recent generative AI and energy report involving something called the Volve dataset.
what happened there?
A forward-thinking company integrated a customized Gen AI chatbot directly with their massive archive of historical PDF drilling reports. Now, PDFs are notoriously difficult to extract clean data from at scale because the formatting is essentially just a flat picture of text.
Right, it's not a spreadsheet. But the AI didn't care. It extracted the data from several thousand of these daily reports, structured it cleanly into a database, and then performed a massive comparative analysis across all of them.
Exactly.
It was looking specifically to identify which historical wells had significantly higher non-productive time, which the industry calls NPT.
Right, and NPT is the absolute enemy of profitability. It means the rig is rented, the crew is paid, but the drill isn't turning because something is broken.
And the AI combed through thousands of PDFs to find exactly which repair events or fishing events, which is when a piece of the drill breaks off and they literally have to fish it out of the hole.
Yeah, those are awful.
They found exactly which of those events were causing the most delays.
To execute that specific comparative analysis manually would take a dedicated team of engineers several months of tedious reading and spreadsheet entry. The AI chatbot accomplished it in moments.
Unbelievable.
It compared one company's operational statistics with another, generated clear visual charts, and identified exactly where operational protocols could be improved based on historical failures. It literally turns dead, forgotten text into predictive, profitable intelligence.
It's incredible. But it's not just text, right? We are moving from AI reading historical words to AI actually looking at visual and physical data. Let's transition from generative AI to computer vision and look at the fascinating world of synthetic cores.
This takes us from the macro level of reading thousands of reports down to the absolute micro level of analyzing the physical rock itself, pulled straight out of the earth.
Let's set the scene with the process of core logging. For anyone who hasn't been on a rig, when you drill an exploratory well, you don't just grind the rock into dust. You use a specialized hollow bit to extract a solid cylindrical sample of the intact rock, called a core.
It looks like a long stone pillar.
Right. Geologists then lay these cores out in long boxes, and they have to meticulously look at every inch of this rock and manually log its lithology, what kind of rock it is, its chemical alteration, its fractures, and its structures.
And as the experts from the AI company DataRock rightfully point out, logging core manually is an incredibly time-consuming, physically exhausting process.
I can imagine.
It is also inherently subjective and highly inconsistent across different human teams. One geologist might interpret the exact boundary of a mineral alteration zone slightly differently than the geologist working the next shift.
Right, human error.
Exactly. When you multiply those tiny subjective differences across miles of core samples, the entire 3D model of the reservoir becomes blurry.
But now you have specialized tools like DataRock and Litholens using advanced computer vision to automate this completely. They take ultra-high-resolution imagery of the drill core, sometimes taken from televiewer tools lowered directly into the borehole, literally taking video of the walls.
Yeah.
And the AI extracts and classifies the geological features pixel by pixel. It provides structured mathematical outputs that integrate directly into the company's 3D models.
And they employ what they call a geologist-in-the-loop design. This is a crucial distinction. The AI is not attempting to replace the expert geologist. It is creating a repeatable, mathematically consistent baseline standard.
It's an assistant.
Yes. It frees the human expert from the exhausting box-by-box grunt work of routine logging. It highlights the anomalies and says, look here, so the geologist can focus their energy on high-level interpretation and strategic insight.
Okay, but I really want to stop and push back on something here, because this next part absolutely blew my mind when I read the research from the John Lab.
Oh, the Jans.
Yeah, because physical core recovery is incredibly expensive, right?
Yeah.
You have to stop drilling, pull the whole pipe out, put the special bit on, go back down. And sometimes you get poor recovery rates. Yeah. The rock is crumbly, it breaks apart, and you pull up an empty tube, leaving you with massive, expensive gaps in your geological data.
That is a highly frustrating but very common problem, particularly when drilling in highly fractured or data-scarce environments. You spend all the money, but you don't get the rock.
So to fix this missing data problem, the John Lab developed a machine learning solution using generative adversarial networks, or GANs. They take the data from a tool called a formation microscanner, or FMS.
Right.
Now, the FMS doesn't take pictures. It's a tool that drags along the walls of the borehole and provides detailed electrical resistivity-based maps. It measures how well the rock conducts electricity. The John Lab feeds that purely electrical data into the GAN to literally generate highly realistic synthetic images of what the core would look like if they had successfully extracted it.
It's fascinating.
Wait, hold on. So the AI is basically hallucinating or imagining what the rock looks like based on electrical resistance.
Yeah.
How can any serious geologist trust a synthetic imaginary rock?
It is a very fair and very common objection. The word hallucination gets thrown around a lot with generative AI, usually in a highly negative context, meaning the AI just made something up. But to understand why geologists trust this, we need to calmly break down the actual mechanism of a GAN. A generative adversarial network involves two separate neural networks locked in a continuous mathematical contest with each other.
Okay, break that contest down for me.
Think of it like a master art forger and a brilliant detective.
Okay, I like that.
The first neural network is the generator, the forger. Its job is to create a fake image of rock texture based on the electrical data. The second neural network is the discriminator, the detective. Its job is to evaluate that fake image against a massive training dataset of real, known rock cores.
So the forger paints a rock and the detective says, no, that looks fake.
Exactly. The detective says, no, the shadows are wrong. Sandstone doesn't fracture like that at this electrical resistance. So the forger tries again and again. They fight each other millions of times a second.
Wow.
The process only stops when the generator creates an image so mathematically perfect that the discriminator literally cannot tell the difference between the synthetic image and a real photograph of a rock.
So it's not just a random guess. It's a mathematically proven correlation.
Yeah, a guess at all. It is a statistically rigorous synthesis. The John Lab trained the AI extensively on thousands of historical examples where they had both the physical core in a box and the FMS electrical resistivity logs for the exact same depth.
Oh, so they had the answer key.
Yes. The AI painstakingly learned exactly how specific electrical resistivity patterns, how electricity flows through the microscopic pores of the stone, correlate to specific visual textures, grain sizes, and fabrics of sedimentary rocks.
It learned the hidden underlying relationship between electricity and visual rock texture.
Yes. So when they give the trained Jan a new set of FMS data where a physical core is missing, the Jan generates a synthetic core image based entirely on those proven mathematical correlations. It is acting as a bridge between abstract wireline logs and physical geology.
It is just brilliant.
It provides a high-resolution visual insight into the subsurface that is vastly superior to having a gap in the data. It reduces the reliance on expensive physical core samples while offering geologists a scalable, highly accurate way to classify geological facies without ever pulling a rock to the surface.
Wow. Okay, that forger and detective analogy makes perfect sense.
Yeah.
So computer vision and JANs are helping at the extreme micro level, looking at the grains of the rock itself. But deep learning is also revolutionizing the massive macro level view. Let's zoom way out. We are talking about mapping entire underground mountain ranges using seismic data.
Seismic interpretation is perhaps the most computationally heavy, expensive, and critical step in the entire exploration workflow. Before you spend $100 million drilling a hole, you need to know exactly what the structure looks like.
Right. And for you listening, seismic data is basically an ultrasound of the Earth's crust. They create massive acoustic shock waves at the surface using explosive charges or those huge vibrating trucks. And they record how those sound waves bounce off the different layers of rock miles down.
Yeah.
Traditionally, geophysicists spend months, sometimes years, manually analyzing these complex, wiggly lines, looking for subtle amplitude variations that might indicate a hidden fault line or a porous reservoir trapping oil.
It is incredibly exhausting, tedious work. You are staring at screens of gray and blue static, and human eyes are naturally susceptible to bias and fatigue. After staring at seismic lines for 8 hours, you can very easily miss subtle, critical discontinuities hidden in the environmental noise of the data.
But now we have machine learning models from companies like Subsurface AI and AspenTech stepping in. They're completely automating fault and horizon detection. What used to take a team of geophysicists, weeks of manual line-by-line interpretation, is now being completed by algorithms in a matter of hours.
It's incredible.
And the metrics on this are just staggering. Modern deep learning is accelerating seismic interpretation by a factor of 10 to 1,000 times.
Let that sink in. 1,000 times faster. A project that took 3 years now takes a single day.
I want to direct a question to you, the listener. Think about what you do for a living, whatever your daily tasks are. Now imagine a piece of software coming along that does your exact job 1,000 times faster.
Yeah, it changes everything.
That alone is disruptive. But here is the kicker. In the case study provided, the automated machine learning algorithm achieved 92% accuracy compared to the initial manual interpretation. But when the human experts were asked to perform a second manual interpretation of their exact same data a few months later, their consistency with their own first interpretation was only 91%.
Right. The machine is not just faster, it is statistically more consistent than the human expert revisiting their own work. It doesn't get tired, it doesn't have a bad day.
So what does that mean for the human worker?
It means the nature of their job fundamentally changes. AspenTech's Dr. Bruno de Rebet discusses this evolution at length. The AI acts as an amplifier for the geoscientist's capabilities.
Right, it doesn't replace them.
Exactly. It handles the heavy computational lifting, the repetitive pattern recognition, and the raw data sorting, while the human expert focuses on validating the outputs and applying the broader creative geological context that the machine cannot understand.
Dr. de Rebet specifically highlighted AspenTech's proprietary multi-resolution graphic clustering, or MRGC, alongside their self-growing neural networks. These tools analyze multiple seismic attributes. Simultaneously, they look at the amplitude of the wave, the phase, the frequency, all at once. How are these algorithms finding geological structures that human geophysicists simply can't see?
Because human vision is strictly limited. We see in 3 dimensions, and we only process a very specific spectrum of light, contrast, and color. The MRGC algorithm is not constrained by biology.
It sees the math.
It can identify mathematical clusters within the data across multiple dimensions and at different resolutions simultaneously. It can spot a microscopic anomaly or massive geological trend at a scale that the human eye literally cannot perceive in a traditional 2D visual slice on a monitor.
That's wild.
It establishes the complex mathematical relationship between the known rock types at the wellbore and the abstract seismic data to create a highly probable 3D rock-type distribution map across the entire seismic grid.
And the John Lab is doing incredible work on this front, too. They developed a convolutional neural network model named SRTAI, which stands for Seismic Reflection Terminations Attribute. That is a mouthful, but what it does is amazing. They trained the CNN on 160,000 synthetic, computer-generated seismic models.
And the performance of that training is remarkable. On the synthetic test data, it achieved 99.9% accuracy.
Crazy.
But the real test of any AI is how it handles the chaos of the real world. More importantly, SRTAI demonstrated incredibly strong generalization when applied to real-world, highly noisy datasets from the ocean floor off northwest Australia.
How did it do?
It achieved 91% accuracy and 96% precision on real, messy field data. It provides automated, scalable, and instant identification of hidden seismic boundaries.
It's reducing the massive costs of having to reshoot poor seismic surveys. It's filtering out the environmental noise, and it's making early-stage exploration reconnaissance incredibly consistent.
Absolutely.
So we've essentially created a perfect, high-definition 3D map of the subsurface using AI. But a map is completely useless if you crash the car trying to get to the destination. How do you take this perfect digital model and translate it into a massive physical steel drill bit grinding through rock without breaking? That brings us to the operational phase. From screen to rig, real-time drilling optimization.
This is where the rubber meets the road. We transition from exploration, finding the resources on a computer screen, to extraction, the violent physical reality of getting them out of the ground. And IT companies are proving to be just as vital on the dirty rig floor as they are in the sterile data center.
We have a fascinating paper here published by the American Association of Drilling Engineers, the ADE. It details the real-world implementation of an advanced AI-driven tool designed to optimize drilling performance. They tested it on 3 active wells in a West Texas project, specifically drilling into the highly challenging Brushy Canyon and Bone Spring rock formations.
Oh, those specific formations are notorious in the industry. They consist of interbedded layers of hard and soft rock that cause accelerated, severe bit wear and severe vibrations.
This destroys the equipment.
Exactly. They require highly specific, constantly changing operational solutions to mitigate catastrophic risks like hole washouts, where the sides collapse, or complete tool string failures, which can cost millions to fix.
The mechanics of this predictive drilling platform are incredible. The AI sits on the rig and monitors data streaming in real time right from the sensors directly behind the drill bit. It watches 3 main things: weight on bit, or WOB, which is exactly how much literal downward force the rig is pushing onto the drill; rotary speed, or RPM, which is how fast the bit is spinning; and mud flow rates, which is the specialized fluid they pump down to clear the crushed rock cuttings out of the way.
And the AI doesn't just watch these numbers in isolation. It takes this live, second-by-second data and instantly compares it against a massive database of historical offset well data, meaning data from other wells previously drilled in the exact same formation.
Let's translate this into an analogy. Think about using a hand drill on a really tough, unpredictable piece of wood. If you push too hard, too much weight on bit, but you spin the drill too slow, the bit gets completely stuck. If you spin the drill incredibly fast, but you don't push down, you just create friction and burn the wood, ruining the bit.
Exactly.
AI is finding the exact, perfect mathematical sweet spot of pushing and spinning for every single inch of rock.
That is a perfect visualization. The AI creates dynamic performance envelopes tailored specifically to the rock formation the bit is currently grinding through.
So it adjusts as it goes.
Right. By continuously analyzing the historical rate of penetration, how fast the bit moves against the mechanical specific energy, how much energy is being wasted on vibration and heat, it categorizes the drilling performance into optimal quadrants.
Okay.
If the live drill bit suddenly hits a harder layer of rock and starts moving out of that optimal quadrant into a danger zone, the AI doesn't just record an error. It provides probabilistic, actionable recommendations to the human drillers instantly.
It's essentially like having a highly advanced GPS in your car that doesn't just show you the map, but literally retunes your engine and adjusts your suspension in real time as you drive from smooth asphalt onto jagged gravel.
That is exactly what it is doing. It adapts the machinery dynamically to the unseen subsurface conditions. And crucially, it provides preemptive alerts.
Oh, like early warnings.
Yes, it analyzes the microvibrations and tells the drilling engineers, based on these vibration and pressure metrics, you are about to destroy this drill bit. You need to pull up and replace it right now before it shatters at the bottom of the hole and causes a major fishing operation.
And the results from this specific West Texas project are undeniably huge. By strictly following the AI's real-time parameter adjustments, the crew dramatically reduced the total number of bottom hole assemblies they burned through. The BHA is the massively expensive array of cutting tools and sensors at the bottom of the drill string.
Very expensive.
They reduced the required BHAs from 12 down to just 8. They improved the overall drilling efficiency by 30% and reduced catastrophic operational risk by 25%.
It's a massive, immediate capital saving, and you see similar highly impactful AI applications in the completions phase, which is how you prep the well to actually flow. A company called Enverus built a platform called Transform, which uses MVStats, a multivariate analytics engine.
What does that do?
It allows the geosciences teams to combine incredibly disparate multidisciplinary data, seismic maps, well logs, chemistry, and historical production data to rapidly test complex what-if scenarios.
Right. They can use the AI to analyze exactly which geological variables and which engineering designs have the most influence on final oil production. A senior geologist at a major E&P company cited a case study where using Transform's multivariate analysis on a test well in the Utica Shale resulted in a 25% to 50% improvement in estimated ultimate recovery, or EUR.
That's a massive jump.
They used the AI to balance the massive costs of the completion designs, like how much sand and water to pump, with the ultimate output of the well, achieving near-perfect economic efficiency.
And achieving this level of supreme optimization on the rig brings up a critical, often overlooked secondary benefit. Optimizing these drilling parameters doesn't just save the company money and time, it saves massive, measurable amounts of energy.
Which naturally pivots the conversation toward our final major topic, the broader horizon of the energy transition and sustainability. It's because, let's be totally honest, when people hear about advanced AI being deployed to drill for oil and gas faster and more efficiently, a lot of people immediately and rightfully think about the broader environmental impact.
Sure.
But what is truly fascinating is that the very same IT tools, the exact same AI algorithms we've been discussing, are proving to be absolutely pivotal for the green energy transition.
If we step back and connect this to the macro-level global picture, the transferability of this deep geophysics knowledge is absolute. The physics of the Earth's crust, the behavior of fluid moving through porous rock, the management of immense pressure miles underground. These physical laws remain exactly the same, whether you are trying to take carbon out of the ground or whether you're trying to pump carbon back into the ground for permanent storage.
Exactly. Look at Subsurface AI, the company that sped up seismic reading by 1,000 times. The exact same machine learning software modules they use to map hidden oil reservoirs are currently being aggressively repurposed for CO2 geologic storage. They offer a full-cycle workflow solution for selecting safe underground CO2 storage sites, mapping the containment reservoir, characterizing the integrity of the cap rock, and critically actively monitoring the site for decades to ensure there are no leakages.
AspenTech's Dr. Deribet emphasized this exact transition as well. Their self-growing neural network techniques, which cross-equalize different vintages of old seismic data, are perfectly suited to analyze how an underground reservoir physically responds to the massive pressure of CO2 injection over time.
Right, checking the pressure over years.
They can derive complex seismic facies volumes to look for the tiniest, most suspicious anomalies that might indicate a microleak long before it becomes an environmental hazard. This deep Earth AI technology is already contributing heavily to geothermal energy exploration, the safe planning of nuclear waste disposal, and large-scale natural gas and hydrogen storage.
And speaking of natural gas, we really should address the concept of local shale gas, acting as a transitional fuel bridge. Now, to be absolutely clear to you, the listener, I am neutrally reporting the perspective and the findings of the research sources provided here regarding shale gas and its environmental implications. We are not taking any political or ideological sides on energy policy.
Right.
But from a pure data and emissions perspective, the John Lab recently published compelling research showing that utilizing locally sourced shale gas significantly reduces the massive carbon footprint associated with the international oceanic transportation of imported fuels.
The engineering challenge, however, is that extracting gas efficiently from highly heterogeneous, unpredictable shale formations is notoriously difficult. To find the sweet spots, it usually requires a massive amount of exploratory drilling, which undeniably creates its own heavy environmental footprint on the surface.
But this is where the AI steps in to minimize that footprint. The John Lab applied advanced machine learning algorithms to thousands of historical well-logged datasets across 7 major U.S. shale plays. They found that something called random forest classifiers vastly outperformed all other statistical methods in accurately predicting whether a well would be successful before it was even drilled.
To clarify for the listener, a random forest classifier is an AI method that essentially operates like a highly educated democracy.
How so?
Instead of relying on one single decision tree to make a prediction, the AI creates hundreds or thousands of different decision trees, feeds them slightly different slices of the data, and then has them vote on the most likely outcome. It prevents the model from being overly biased by one weird data point.
It's like asking 1,000 different geologists for their opinion and taking the consensus. And by using this democratic random forest, the AI achieved a staggering 97% accuracy in forecasting the initial production rates of wells based on complex geological features like play thickness, pore pressure, and total vertical depth.
That 97% accuracy metric is absolutely crucial for sustainability. It means energy companies can precisely mathematically identify highly productive wells and vastly reduce the amount of blind, unnecessary exploratory drilling.
That's a huge deal.
You drill significantly fewer holes in the ground, you disturb far less surface area and wildlife habitat, you consume thousands of tons less steel and concrete, and you drastically reduce the overall environmental and carbon footprint of the extraction process.
We can see the direct, immediate environmental benefit of AI right there on the rig floor, too. Returning one last time to that ADE paper from West Texas, the AI that was constantly optimizing the weight on bit and rotary speed didn't just drill the well 30% faster to save money. By keeping the massive drill continuously running in that optimal low vibration efficiency quadrant, it actually reduced the raw energy consumption of the entire drilling rig by 8 to 10%.
And that is not a trivial number. A modern drilling rig runs on arrays of massive industrial diesel generators. A reduction in raw energy usage of 8 to 10% translates directly to an 8 to 10% reduction in actual carbon emissions pouring out of the exhaust pipes for the entire duration of the drilling operation.
So what does this all mean for the big picture?
Well, it means the relentless drive for economic efficiency, driven by IT and AI, is now inextricably linked to improving sustainability metrics.
It's an incredible synergy. We have covered a truly massive amount of ground today. We started with the chaotic image of geologists drowning in 10 terabytes of siloed, incompatible data every single day, completely unable to do their jobs.
Yeah, the dark ages.
We saw how global IT companies are breaking down those proprietary silos using the open source OSDU standard and moving that data to high-performance cloud-native environments that unlock limitless compute power.
We explored how generative AI and intern-like chatbots are rapidly reading through decades of unstructured historical reports to find hidden operational efficiencies. We saw how computer vision and the Forger Detective contest of Jans are augmenting physical core logging by mathematically predicting rock textures from invisible electrical resistance.
We saw convolutional neural networks speeding up massive seismic interpretation by a factor of 1,000, finding microscopic structural patterns the human eye literally cannot perceive. And finally, we tracked how all that perfected data moves directly to the rig, optimizing the grinding drill bit in real time, saving millions of dollars and significantly reducing carbon emissions simultaneously.
But the central grounding theme binding all of these incredible technologies together is the concept of the human in the loop. Across every single platform we analyze today, from Datarock's core imaging to AspenTech's seismic clustering to the rig floor AI, the machine is not replacing the geoscientist. It is removing the crushing, soul-destroying burden of data formatting and grunt work, and it is augmenting human intuition and creativity with absolute statistical certainty.
It finally lets the scientists actually do science again. But before we wrap up today, I want to leave you, the listener, with one final, deeply provocative thought, something to really mull over as you go about the rest of your day. Throughout this entire deep dive, we've talked about predictive models and real-time adjustments based on past data, but the future horizon, as hinted at by forward-thinking companies like SBR Energy, is the concept of the self-learning geological model.
It is the ultimate mind-bending culmination of every single technology we have discussed today.
I want you to imagine a high-definition 4D subsurface map of the entire Earth, a digital twin of the crust that isn't just a static picture. Imagine that it is continuously, autonomously updating itself in real time.
That's wild to think about.
Every single time a drill bit touches rock in Texas, or a seismic acoustic wave is recorded in the North Sea, or a temperature sensor drops a degree in the Middle East, that data instantly streams to the cloud. As the algorithms ingest millions of new global data points daily, the model of the Earth learns, shifts, corrects its past mistakes, and refines its predictions without a single human intervention.
It becomes a living, breathing, constantly evolving digital twin of the Earth's hidden subsurface.
Exactly. I want to sincerely thank you for joining us on this deep dive into the muddy, data-rich world of subsurface intelligence. And I want to leave you with this final question. Once that living, self-learning digital model of the Earth is finally complete, what other invisible secrets buried miles beneath our feet in the dark might the Earth finally reveal to a digital mind? Keep questioning, keep exploring, and we will see you on the next deep dive.